And next up, we have Sanae Kubota of GHU APL presenting Parker Solar Probe Continuity of Control on-orbit case studies. Sanae, it's all yours.
All right. Hello, everyone. My name is Sanae Kubota. I am the Parker Solar Probe Fault Management Lead and also the Deputy Spacecraft Systems Engineer. I am not a software person. And if that was not enough to make me feel wildly inadequate to be presenting today, I also don't have anything prepared as a live demonstration. So I'm sorry. Apologies for that. Start out with a quick summary of fault management. So my quick elevator spiel or whatever that I give to describe fault management is it's my job to design the system so the spacecraft can save itself in the event that anything goes wrong. It's an overall system design function, and then the requirements for implementing that design then get allocated to subsystems like autonomy, flight software, avionics, etc. So I'm going to call this talk software adjacent, since a lot of the fault management design does get implemented by autonomy. And we can reference back to Adrian's presentation just a couple of talks ago. And some parts of the design are implemented by flight software. So moving beyond the title slide. Oh, you have control. Could you please go to the next slide? Thank you. So I'll just spend a few minutes up front with a brief introduction to the Parker Solar Probe mission. These are the science objectives. One, to trace the flow of energy that heats the corona and accelerates the solar wind. To determine the structure and dynamics of the magnetic fields at the sources of the fast and slow solar wind, and explore mechanisms that accelerate and transport energetic particles. Phrased a little bit differently in a language that's a little bit easier for me to digest anyway, these same questions are, why is the corona much hotter than the solar surface? So it actually gets hot. It gets hotter the further you move away from the core. Where does the solar wind originate and how is it accelerated? And how are solar energetic particles accelerated and transported? Next slide, please. Okay, so for a quick mission design overview now. We had a 20-day launch period in the summer of 2018 and launched on August 12th, 2018 on a Delta IV Heavy. Our trajectory takes us through 7 Venus gravity assist flybys, each lowering our perihelion distance so that after those 7 steps, we'll fly to within 10 solar radii. And we don't have any deterministic deep space maneuvers. In total, we'll do 24 orbits at least, but that's what the mission is, 24 orbits, 3 with that minimum perihelion distance. The first Venus flyby we did less than two months after launch, and the first perihelion was only 1 month later. So that was a highly terrifying time, but thankfully it all went very well. We are now on our 11th orbit with 5 Venus flybys under our belt. The next Venus flyby actually won't be until over a year and a half actually from now. And then the next and final one will be a little over a year after that in November 2024. The first time the spacecraft will fly at its minimum perihelion distance is on Christmas Eve of 2024. That'll be a little under 6.5 years after launch. And then the next 2 orbits and minimum perihelion passes should happen very soon thereafter. That will have us completing the 3 orbits that fly within 10 solar radii and about 7 years after launch. So that's the quick summary. Next slide, please. All right, for the spacecraft overview. Our instrument suite was selected by NASA to address those science objectives that we talked about earlier. The spacecraft itself, or observatory, is about 3 meters tall and is protected by a 2.3 meter wide shield that we call the thermal protection system. And that's, if you're looking, I guess I don't have a pointer, but if you're, do I rotate? I'm not going to mess with this. Over here on the left, that's the thermal shield, and we need to keep the rest of the spacecraft body behind it. So the spacecraft bus is down below. You see the pointer to the solar array wings, and behind that is the spacecraft bus. The radiators are in between spacecraft bus and the thermal protection system. And on this diagram, they're labeled as the solar array cooling system, which is also correct. Parker Solar Probe is the first spacecraft to fly actively cooled solar array wings. They flap and feather to control the amount of solar input they see and have water coolant lines running through them, which collect the heat and bring it up to shed through the radiators. Fun fact, we actually ended up blanketing some of the radiator area a little bit before launch to make sure that the spacecraft that we designed to dive in and out of the sun doesn't shed too much heat and freeze when it's at further solar distances. So the bulk of my job as fault management lead boils down to making sure we keep the spacecraft bus and enough of the solar arrays behind the thermal shield and keep the cooling system working properly. This needs to happen while it's speeding through space at literally record speed. Last year, we broke our own speed record again, traveling at almost 365,000 miles per hour. With each Venus flyby, the spacecraft picks up speed, and it will eventually travel at over 430,000 miles per hour. Next slide, please. Thanks. So this is a quick snapshot of where the spacecraft is now, or at least as of last Friday when I grabbed these screenshots. On the left, we've got a plot of solar distance versus the days since launch. And so it shows that we've done 10 solar encounters so far, and it shows the 5 step downs of the maximum solar distance, which correspond with the 5 Venus flybys that we've executed. And it also shows that we're headed in now for our 11th solar encounter. On the right, we have the view of the solar system, inner solar system, showing the orbits of Earth, Venus, and Mercury in white, and the PSP orbits are in green, with the final orbits shown in red. For another perspective on speed, that diagram on the right shows that as of this past Friday, the spacecraft was about halfway between the Venus and Mercury orbits. 3 weeks from this past Friday, it'll be on the other side of the sun at perihelion. So that's quite some distance and not a lot of time. All right, next slide, please. So now to dive more in beyond the spacecraft overview and mission overview for some fault management perspective. So keeping the spacecraft safe and healthy as it does all of those crazy things that I talked about earlier is all about maintaining continuity of control. And that is what drove the fault management design. Mission power and thermal constraints require continuous solar array wing angle, cooling system, and attitude control. PSP's design relies on autonomous fault detection, diagnosis, and response. We do have an amazing mission operations team, but reliance on ground intervention for fault resolution for solar probe is precluded due to short fault resolution time requirements, long spacecraft Earth distances, and extended periods of link unavailability. So to support the need for continuity of control, we've implemented a unique 3-processor avionics architecture, which ensures that the hot spare processor is available to assume control within 2 seconds in the event of a prime processor reset or fault. Next slide, please. So the way we do that is with the Avionics redundancy controller. It provides hardware management of the 3 single board computers and contains 3 identical mode controllers whose output is triple voted. So it uses that triple redundant, triple vote system to control the processor logical states and state transition paths. The way we get the very fast transitions is with the ARC is Avionics redundancy controller, so with its prime and hot spare acknowledge timers. Acknowledge timers are just different words for watchdog, but since the watchdog term was already taken, we went with acknowledge timers. With these timers, the hot spare becomes prime within 1 second if the prime is resetting or unresponsive. And the backup spare would become prime within 2 seconds if the hot spare happens to be resetting at the same time. And we have a status packet sent from the prime to both spare processors at 1 Hertz to support continuity of control through SBC rotations. Next slide, please. Okay, so we've seen the system work well in flight. The spacecraft has executed 5 processor rotations on orbit. 3 were ground commanded to address an early Ka-band downlink issue and for flight software updates. And 2 were commanded by autonomy. And that rule has since been disabled during the initiating event. And I know it's important to our flight software team to note that these were all commanded resets. So I do want to make that point. A reset command is used to initiate the prime processor demotion. And then the ARC executes the state transitions when the prime, because it's resetting, fails to check in with its acknowledged timer. So all 5 of those rotations were executed as designed, and each processor has successfully served as prime twice so far in our mission. That's it for this slide. Next one, please. Thanks. Okay, so next I'll address some of the protections used for continuity of attitude control. Parker Solar Probe has experienced occasional star tracker dropouts in flight due to environmental effects. Many thanks to Adrian Hill, who spoke earlier, for this great plot that depicts at what solar distance and which orbit each of the tracker dropouts occurred. In all cases, autonomy detected the condition quickly and quickly promoted the star trackers back into their nominal operating mode. During these brief star tracker outages, the guidance and control software propagates the attitude solution, and so there is no impact to spacecraft health or safety during these events. Next slide, please. So here is a different kind of star tracker related caretaking response that happened in flight. In February of 2019, we saw that Star Tracker 2 had exceeded its power utilization threshold. This happened during a high rate data downlink period, and the spacecraft was tilted to point the high gain antenna toward Earth, which then increased the solar illumination on Star Tracker 2. At the same time, the Ka-band tweeter, which is located near Star Tracker 2, was operating for downlink. So the increased Star Tracker 2 temperature for both of those reasons caused excessive Star Tracker thermoelectric cooler usage, and that's why it exceeded its power utilization threshold. Autonomy detected this anomalous condition and protected the tracker by powering it off. After that event, we added further protections. So further autonomy protection and operational constraints to preclude operation of Star Tracker 2 during Ka-band tweeter use when the spacecraft tilt exceeds a threshold. So at a threshold where we have the potential to overheat, we've precluded that condition. Next slide, please. Okay, now for continuity of solar array wing angle control. The flap and feather movement of the solar array wings manages the solar load that the wings see, hiding the rest of the wings in the shadow behind the thermal shield. It does this to prevent overtemperature, undertemperature, low battery state of charge, and to accommodate spacecraft attitude changes. Control of the wing angles is implemented through the guidance and control flight software with inputs from the power system and a fleet of temperature sensors. Actuation is controlled with the very generically named Electronic Control Unit, or ECU. The ECU has redundant command and telemetry interfaces to stepper motors and potentiometers, and it is cross-strapped to the redundant spacecraft avionics. So each ECU can talk with both avionics sides. The ECU actively listens to both UART interfaces and responds to the avionics side that sends the telemetry request command. And for the most part, that works very well. But next slide, please. So again, for the most part, it works very well, but there was an ECU FPGA implementation error that results in the ECU interface locking up in the event that it receives only a partial command. And So an LVDS glitch is interpreted as a start bit for the first command byte, so that's just a partial command. This issue was observed in pre-launch testing, and all identified potential fault scenarios were mitigated pre-launch. However, PSP has experienced 2 in-flight occurrences when the active ECU stopped responding. Following those, we got back in touch with the vendor, and they helped us troubleshoot. Their vendor simulations have reproduced the anomaly and indicate the likely cause to be an LVDS glitch. The root cause has not been identified. And flight data is consistent with the LVDS glitch fault signature. But the good news is the in-flight fault detection and response were executed immediately and flawlessly, switching to the redundant ECU and enabling continuity of solar array wing angle control. Just another demonstration of the great execution of the autonomy system that Adrian was talking to earlier. And next slide, please. Okay, so you can see I'm not going to use up a lot of my time, but because I'm moving on now to the final example for today, which is of protections that were put in place to ensure continuity of control is continuity of control for maintenance of mission elapsed time, or MAT. So spacecraft target attitude is determined based on a combination of MET and the onboard ephemeris as the primary method. And we also maintain an MET-based table of solar distances as backup. To support this dependence that we have on MET, we store it redundantly in all 3 SBCs and the active spacecraft interface card, which is the SCIF. What I'm showing up in the diagram in the upper right is the point here is that the SCIF uses the primary radio's precision oscillator as the time basis for mission elapsed time, and uses that to send time codes out to the single board computers. Let's see what else here. Then down below in kind of this quad chartish thing, in these 4 boxes is a description of how we respond to different fault conditions depending on what the scenario is at the time. On the next slide, I will talk to one of those in particular. Okay. So recall that the spacecraft interface card uses the primary radio's precision oscillator as the time basis for the time codes that it sends to the processors. Well, in November of 2019, the primary radio reset. By design, flight software suspends the bus schedule if time codes are missing. And that then leads autonomy to switch avionics sides. And so that's the first thing that we saw. Unexpected radio reset was also flagged, indicating the cause for the dropout of time codes. In this scenario, we have autonomy evaluate the health of the radio's precision oscillator and confirm that it's functioning well before returning to put it back in charge as the time basis. Autonomy did this, and we saw that the MET maintenance chain, including flight software, autonomy, and hardware, protected the spacecraft flawlessly as designed. Next slide, please. And I think that might be it. Yeah, so that's all I've got. Through the 10 orbits so far, we've seen that the Parker Solar Probe fault management system, including all responsibilities that have been delegated out to hardware, flight software, and autonomy, has performed as designed, successfully managing on-orbit events to keep the observatory safe.
All right, thank you, Sanae. Looks like we do have a few questions to go through. So the first one is, what's the reason behind the scheduled processor rotations? Does the primary processor have to do more work, so it needs to be protected from aging?
So we don't have scheduled processor rotations at all. We do try to avoid them. Yeah, so that might answer the question. We have had 5 on orbit, but they weren't scheduled. They were in response to events.
Okay. Next question. How much does clock drift affect the mission elapsed time?
Oh, goodness. I used to know these numbers. I'll say a very small amount in lieu of remembering the numbers. I will say that the way that we addressed how we respond, the requirements that we put in place to respond to MET, I guess, glitches or needing to transfer sources from one to another, we needed to accommodate potential drift on a course oscillator through, I think, for our secondary launch window, so the backup one, not the one we actually launched on. It was something like our longest potential comm outage was, I think, something like 64 days. So we needed to accommodate being able to drift for that duration and still have the resulting MET accuracy to be able to point appropriately through solar encounter. So it is a very small number, but I don't remember anymore. Sorry.
Yep, okay. Next question. Since at every flyby the velocity is increased, your target performance processing rate is determined by the 24th flyby. What if the duration of the mission exceeds the planned one?
Target performance processing rate. Because I'm not sure.
Yeah, is the guidance and control or pointing performance determined by the 24th flyby, or is there any impacts from an extended mission, I think is the question.
It doesn't vary with speed. I guess is the way I would answer that.
Okay. Next question. Is there a special coolant mix used for the solar cooler system?
So oddly enough, and this trade study predates my time on Solar Probe, even though I was almost there from the beginning. But oddly enough, our coolant is actually water. From what I understand, the trade study involved, I don't know, close to 100 different fluids that they evaluated. But as I mentioned when I talked to the fact that we blanketed part of the radiators a little bit before launch to make sure that we didn't freeze, we are a little bit, well, we're unique in a lot of ways, but one of the unexpected ways is that we do fly far out from the sun as well as close in. So it was a matter of finding a fluid that does well both at like very hot temperatures as well as colder extremes. And turned out that water was actually the best fluid. So that's what we have.
Okay, great. Give a few seconds for any more questions to filter in. Okay. Thank you very much, Sanae. We really appreciate it.
No problem.
All right.